Good afternoon, Sandeep ji. Dear participant, I am audible.
Yes, sir.
Thank you, thank you, thank you. Dr. Oja, are you there?
Yes, sir, I'm here.
Thank you. So, I welcome you again, all the participants, in this day 2, session 2 of this week-long FDP program that is supported by ATAL AICT scheme and conducted under the institution of IIITNR. We are going to start our session 2, and with us, as I already discussed in the session 1, we are going to have a 2 consecutive session based on the deep learning neural network, and the session 2 will be on the CNN, and the last session of the today from 3 to 5 will be on the RNN. And I also talk about the resource person of these 2 sessions, that is the Dr. Munendra Jha. So, sir, I welcome you in this session and invite you to give your knowledge and information to all the student, the participant, research scholars, and faculty members. Dr. Oja is my best friend. He was associated with the IIITNR Raipur in couple of months back. He joined the IIIT Allahabad, but we are still together. We have applied and completed many research projects. We are working in many projects, research papers. We are guiding the student together in the same PhD scholars, MTech scholars. And so in this view, I welcome Dr. Oja. Without wasting any time, I request to you, please kindly take up the charge and please start your session, please.
Thank you, sir. Thank you so much for the introduction and thanks for your friendship. As always, I always cherish it. Here, I would like to take this opportunity and beg your apology for logging in through 2 systems, one the mobile mode and another my desktop. My desktop does not have webcam, so I have to use the mobile. So I'll be using the 2 modes, but I promise that it will not be an interference in the overall presentation and the delivery of the talk. Okay. So with that, I want to take your permission to start the topic of discussion.
Please go ahead. Thank you.
Thank you, sir. All right. Just a second. Unfortunately, due to these work from home things, we are not as organized as we used to be. But anyhow,
Sir, one
so let me.
small update. The one lecture I have taken on the neural network, where the basic understanding I have tried to develop, like layers, architecture, neurons, activation function, net input, and what is typical back propagation and forward propagation. All basic things already covered with the students. So you may start accordingly,
Very
sir,
good.
please. Thank you.
Very good, sir. So as you have mentioned, I'll be talking about the next topic of this talk, the convolutional neural network, and I will assume that participants are already familiar with the basics of deep learning, as you have already covered these. So over in this lecture, let me start. Right. So I am Dr. Munendra Ojha. As told you, I was previously associated with IIIT Raipur. Now I am working at IIIT Allahabad. In this lecture, I'll be talking about convolutional neural networks, which is an advancement over the deep learning fundamental, the foundation of deep learning. And this type of neural network, as many of you might be familiar with the working of convolutional neural networks, is utilized in image processing tasks, image and video processing. Task video processing is nothing but an extension of image processing. So computer vision task as a whole is heavily benefited with the advent of convolutional neural networks. Why this is so much talked about technology, I'll tell you with this example. As you see over here, this is a picture of Barack Obama, and as soon as I opened this slide, I hope every one of you who noticed the slide would have observed that the person whose picture is given over here is Barack Obama. You would have recognized him to be the previous president, former president of United States of America. And then there is a building behind him, the Capitol building, and he is wearing a suit, black jacket, gray tie. He's smiling, and his face is surrounded by a bounding box of color green. All of these things you would have immediately observed and noticed without even thinking. Okay, I'm pretty sure about that. Why? Because human brain since childhood has been trained to recognize human faces. Okay, and since we have seen his face so many times, I am pretty sure that 99.999% of people would recognize Barack Obama. I'm keeping the probability of 0.0001% for the sake of brevity, that we are computer scientists and we are machine learning engineers, and we always claim that our result is not 100% accurate. Okay, so I always keep some error with me. Okay, so this image, the image that was identified as the image of President Barack Obama, former President Barack Obama, does not require any explanation for us to be identified. Why? We did not tell you where is the person in the image. We did not tell you that person is in the foreground and the building is in the background. We did not tell you that person has two eyebrows. We did not tell you there is a forehead, two eyes, vertical section of nose, and then immediately following that a horizontal pair of lips within which there will be a set of teeth. We did not tell you the color of his coat. We did not tell you the color of his tie. We did not even tell you that he is wearing coat and tie. Nothing was specified. Still, the brain was able to identify all of these things immediately. How? Okay. This is a question that is being answered by deep learning. So deep learning does not depend upon these explanations, unlike machine learning, which requires us to give it explanation of what is data, how is data given, what are the features of these data, what are the properties of the data, how the data was collected, what are the values in the data. All these things are the shortcomings of machine learning algorithms. And these shortcomings have been overcome in deep learning. The biggest shortcoming, I would say, of machine learning was that machine learning algorithms needed to be specified what are the features of the data. Okay, the data has to be specified in certain feature, and with every feature, whatever feature there might be, with every feature you have to specify the importance of those features and then weightages of those features, why those features are important, why those features are not important, how many features are those which can be removed, like dimensionality reduction as well. All these things were there in discussion, and they were required because the machine learning algorithm heavily dependent upon features and feature selection. So like in this image, you see, I don't really need to specify that if it is a human face, the human face should have a pair of eyebrows beneath which you need a pair of eyes and a vertical section indicating nose, and then a nose bridge, and then a pair of lips or teeth, so on. The cheeks should be beneath the eyes so that there is a sharp contrast of color from brightness, probably from the color versus the darkness of the eyes. Okay, these things I don't need to specify, these things I don't need to explain to the algorithm. Why should I? Suppose I start explaining these things and a person is not looking straight forward towards the camera. A person might be looking sideways, or let's say the image is of a cartoon or a flyer in which these contrasting brightnesses are not present. Then how would the algorithm be able to identify the human face, right? So this becomes a rule-based algorithm in which the algorithm is just following a set of rules, and those rules are being identified, not the face. We humans are very good in performing something, but we humans are very bad in explaining the way we perform those things. Like, suppose I ask you to write a page of text, okay, one page of text, and then I ask you, how did you write? Explain each and every alphabet that you have written by explaining the cursiveness, and why did you write it in this fashion, while suppose many people write R differently, two or three different ways the small r is written. If you ask somebody to explain why this is r, they will not be able to explain. However, they will immediately understand that this is r. Similarly, if you do something, if you probably perform some activity, then performing the activity, because it has been in your nature, you will be able to perform those activities. Like many ladies would be here who would be performing so many different chores of the home, daily chores, and they will be doing it subconsciously, unconsciously, and they will not be able to explain it to us how they are able to manage it so beautifully. How do they manage these many tasks at home, in office, children, husband, relatives, so many things they manage. But how do they manage it? They'll not be able to explain it, but they do it beautifully. So if I ask you, how did you recognize this to be Barack Obama? Then nobody will be able to explain to me why this image is similar to Barack Obama, right? What is similar over here? Does he have two eyes? That is why it is similar to Barack Obama. Does he have two eyebrows? Certain number of teeth, a lips, pair of lips. His color is brown. He has this curly hair, very short curly hair. He wears black coat and gray tie. That is why. Or his smile is like Barack Obama. What was there in this image that made you make this decision that the image belongs to Barack Obama? We will not be able to explain it. Okay. Similarly, suppose you have seen a person. Okay. Let's take the example of police action. Suppose we have seen a person committing some crime, and I am asked to explain the facial features of the criminal. It will be very tough for majority of us to explain the facial features of the criminal such that a good image can be drawn, right? However, as soon as that person is brought in front of us, many of us, probably a bigger percentage of us, will be able to recognize the person. So what we did over here, we performed the task, but we are not able to explain how did we perform the task. So machine learning algorithm, on the contrary, require us to explain to them how to perform this task, which is very difficult job for us, right? So this shortcoming was actually the feature selection shortcoming was actually overcome by deep learning techniques. Okay, so as it says, the problem is the algorithm hasn't really learned that much about what it means to see a face. So this refers to a Viola-Jones algorithm, in which Paul Viola and Michael Jones published this paper in 2001. And in this paper, they tried to understand what does it mean by a face, a human face. So they identify somewhere like dark and light shade pattern. So cheeks will have a brighter contrast than dark eyes. Then there is a nose bridge between the eyes and the set of lips. There is a horizontal nose bridge. So they try to recognize, they try to featurize the human face. Okay. By themselves, these features were not effective at identifying the faces. However, when combined together with many different machine learning algorithms, they obtain an accuracy of detection accuracy of 91.4%. Right? So the problem it is identifies, the problem is the algorithm is that it hasn't really learned that much about what it means to see a face. Beyond differences in light intensity, our brain uses a vast number of visual cues to realize a human face, including contours, relative positioning of facial features, and color. If there are slight discrepancies in visual cues, for example, part of the face are blocked, if shade modifies light intensity, our visual cortex takes care of that. It can still reliably identify the face, and it can still modify the learning and I didn't understand the inference of the learning that has been fed into its brain, that okay, these changes are because of the natural lighting and the shading effect, and considering all those factors, we still identify the face to be the person whose face is given to us. However, are these features actually going to depict every possibility in any scenario that a face could be identified? No. Now comes the next question. If traditional machine learning algorithms are not suitable for these kind of tasks where features cannot be specified, okay, features cannot be specified, so what about the fully connected regular neural networks, where the neural network is known to identify features of its own? So if neural network can identify features of its own, then what about the regular fully connected neural networks with which we feed the image to neural network and let the neural network decide upon its own features? Okay. So the problem with regular neural network is that first, the efficiency of the neural network. The neural network does not want you to specify these features. Neural network just accepts the input, and then through gradual layer by layer mechanism, by individual working of neuron, it understands the feature, and then it tries to create its own understanding of whatever data is fed to the neural network. It creates its own features. We may call it feature. We used to call it feature because in many application in transfer learning also, we utilize the transformation of input from the original input, from the image input to the final row vector that is given to us as a transformation of the data into feature values. So suppose we are given um, let's say 5 MB of image data, 5 MB of image data, we convert it to probably 20 byte, 30 byte uh, uh, vector, 20 or 30 byte vector, which will be a feature representation, a full feature representation of the image that is given to us. So we transform the image into a set of features. So neural networks are utilized to create its own feature. Whatever image is given to us, neural network will understand the image and then create its own feature. But then I say that regular neural network, the fully connected neural network, is still not very efficient in performing the task. Why? Because you see, when we have regular neural networks, they don't scale well to the full image. Because suppose this is an image of 200 by 200 by 3, where 200 by 200 pixels are the height and width of the image and 3 is the number of channels, it would lead to a set of neurons which will have 120,000 weight values, right? Do you all understand this thing? If the neural network is fully connected, as number of layers increase, the parameters would add up quickly. Therefore, fully connected neural network, the full dense layering is a total waste of the number of parameter, and a huge number of parameter would quickly lead to overfitting, right? And one more thing is that it's not necessary that certain feature will be present in whole image. So we don't really need to understand whole image thoroughly. We need to understand sections of those image where features are present. The image is not something that could be represented by numerical values. Image is something which could be understood by certain feature which are present in certain location of the image. Like in this image, you see the features that are being identified manually, like the eyes. You see, eyes are eyes and they will be present in certain part of the face only. It cannot be, it can never be imagined that eyes will appear in place of lips, or probably two eyes. Instead of two eyes, we will have a Goliath like single eye over here, and another eye might appear somewhere else. Okay, these things do not change. And if nose is present, nose is certain to be present at the almost center of the face, right? So these things are fixed. However, certain features which are not fixed may vary. So it all depends upon what is fixed and what is varying. So with the numerical values, the neural network has to identify the features which are present in certain locations, and those features which are present in throughout the face, okay, throughout the image. Then if it is a location specific feature, then if the feature is present in a certain location, then it should be understand, like teeth. If it is present, a whiteness is present in this location, it should be identified as a set of teeth. If some darkness is present in these location, it should be understood as a pair of eyebrows, and beneath eyebrows should be understood a pair of eyes also, right? So these are the things which are location specific and location dependent, location independent. These things should be identified by the neural network. Now, if the neural network is fully connected, it is actually a wasteful thing. If the feature is location specific feature and it is not present in any other part of the image, then that location should be highlighted instead of just feature being searched in the whole image. To overcome this problem, a concept of convolution, which is very prevalent in computer vision tasks, was introduced in deep learning. What is convolution? Convolution is used in blurring, smoothing of images, edge detection, sharpening of images. All of these methods are convolution method. Convolution is one of the most critical fundamental building block in computer vision and image processing. What does it mean by convolution? Convolution is just a process in which we take two matrices, we multiply those matrices, and then we sum the products of all the multiplications. So in a way, this is a dot product. How do we perform dot product between two vectors? The convolution is nothing but a dot product of two vectors or two matrices. What happens in dot product? In dot product, we multiply the values of respective dimensions, and then those multiplication result values are added together to create a scalar value, right? So as it says, in terms of deep learning, an image convolution is an element-wise multiplication of two matrices followed by a sum. So we take two matrices, both should have same dimension. We multiply them element by element. Okay. It says not the dot product. However, the effect is exactly as the dot product. It's a simple multiplication. When we do the element by element multiplication, it's a multiplication of elements, respective positional elements. And then we sum all the products, or whatever be the multiplication value, we sum all the products together. Like in this example, you see this, if I could stop it at some point, yeah, right. You see over here, I have got two matrices, in fact three matrices over here. One is a big matrix, the green one. Another is a small matrix, the yellow one. With yellow matrix, I see some values written in red. Okay, the black values are written in the green matrix, the big matrix. Okay, this is the big matrix. This one is a small matrix, and the red values are the values of the small matrix, the yellow matrix. What is happening over here is a convolution process that takes place in convolutional neural network. Okay, so try to understand it very carefully, and then you will have a fair idea of what would be a CNN. You see a big matrix and a small matrix. The big matrix is the image. Okay, what we do is that we take a small matrix like this one, which has these red values as its element. So a small matrix, the yellow matrix, has red values as its element. So a small matrix, first element is 1, second is 0, third is 1, 1, 0, 1. This element is 0, 1, 0. Third row has 1, 0, and 1. Okay, so there are 9 elements in the small matrix, tiny matrix, and the big matrix has 25 values. Now I take the small matrix and I put it over here. First, I put it over here. Okay, so I'm explaining to you what happens in convolutional neural network. Now, through that, I will explain what happens in the why it happens and what is the after effect of it. So I take a big matrix I call an image, and then I take a tiny matrix is our filter, which we will call as filter. So tiny matrix is the filter. I take this filter or the tiny matrix and put it over here. Suppose this is the location I have put my tiny matrix. What I'll do is that I'll perform convolution at this step. As previously in the previous slides, I told you convolution is nothing but element wise multiplication of values, two matrices, and then their sum. Okay. So I take elements 1, the red element over here 1, and then this one. I multiply both of them. So 1 into 1 is 1. So let me write it over here 1. So 1 into 1 is 1. Then I take the second element 1 and the second element of tiny matrix 1 into 0 is 0. I don't write it. Third element is 1 and then 1 is multiplied with 1 again plus 1. Right? Then this value is 0. I have to multiply with its respective positional element. So 0 multiplied with 0 is still 0. 1 multiplied by 1 should be 1. This 1 multiplied by 0 is 0. This 0 multiplied by 1 is 0. This 0 multiplied with this 0, 0. Our this 1 multiplied with this 1 is 1. Right? And now I have got these 4 values, which when added give me 4. This 4 comes over here. So the first, when I took this small matrix, tiny matrix, and I put it at the upper left corner of the big matrix, I got a scalar value 4. This 4 is put over here. Similarly, I'll take this and shift it over here, and then this tiny matrix is multiplied with these 9 elements, and the result is 3. Then I take this and shift it over here so that elements, tiny matrix element are multiplied with these 9 values, and the result is again 4. Similarly, I take this and bring it one row below, and in that case I multiply the tiny matrix, these red values, with these 9 elements, and the result is 2. Then I take it over here, take this big tiny matrix and multiply it with these 9 elements, and the result is 4. And in this scenario, I take it over here and then I multiply with these 9 values, and the result is 3. Okay, so you see 1 into 1 is 1, 1 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. So 2 ones, this and this, then 1 into 0, 0, 1 into 1, 3 ones, then 1 into 0 and 0 into 1, 0. So 3 ones, and this results in a value of 3, right? So this is how the convolution is happening, and after every convolution operation, a resultant scalar value is written in the third matrix, which we call as a feature map. Okay, so there is a concept of big matrix. Sorry for this writing because I'm using mouse. Matrix, then small or tiny matrix, which we also call as filter, right? And then this is called feature map. Right? So this matrix, the third matrix that we create out of big matrix image, this is image. The big matrix is image, as is it also written below. This is image. The big matrix is image. The small matrix is filter, right? A small matrix is filter, and this resultant matrix is the feature map. Okay, so I hope the process of convolution is understood to you. Now the concept of big matrix, tiny matrix analogy that I gave, the image, an image is the matrix with a width of columns and height or depth, number of channels, right? If it is grayscale, it will have 1 depth. If it is RGB, then it will have 3 depth and the depth is called as channel also, excuse me. We can think of an image as a big matrix and kernel or the convolving matrix as a tiny matrix. Okay, so there are different names for this tiny matrix. Tiny matrix is called with different names. In mathematics, since it is a mathematical operation convolution, in mathematics it is called as kernel. In image processing tasks, it is called as filter because we will be using it as a filter. Why filter? I'll just explain to you. So it is a kernel or convolutional matrix, tiny matrix. The tiny matrix sits on top of the big image and slides from left to right and top to bottom, applying convolution at each xy coordinate of the original image. Okay. I think I just mismanaged the slides layout. They should not be here. Okay. Let me just rearrange for a second and then I will. This convolution layer should not be here. It is actually the position of it should be. Okay. All right. Let me get back to this one. All right. So I talked about filters and feature maps. Why I am calling this kernel matrix or the tiny matrix, the small matrix, the convolutional matrix a filter, I will explain with this example. You see, the concept of filter arose because whatever matrix we are using it as a kind of viewing window. Okay, I'm taking this viewing window, I'm taking this filter and I'm putting it at every location of the image. Okay, so in this image, you see, I suppose I create a filter. I create a filter, and this is my filter, such that I hide everything. I hide everything, but leave this part open. Okay, let me hide everything. I will shade out everything else except a certain portion of the image. Not taking too much time. I will just click completed. Then yes. Now, suppose this is a viewing pane. I have taken something. Let me use this one. Yeah. So suppose this is my filter. Okay. And this is my tiny matrix. This is my convolutional matrix. I hope you can see this, what I have created over here. I have created a shade kind of thing and I'm going to use it. Okay. So I'm going to use it to look through the whole slide, this PPT slide. So I'm putting it over here. Let's say I'm putting over here. So whatever is shaded region, I'm not able to see anything. Imagine that I'm not able to see anything through this shaded region, but I only see through this white portion. Okay. So if I put over here, let's say, let me put over here. Yeah. So if I put over here, I'm looking at certain alphabet and I recognize it to be F. Okay. Let me just say that I'm looking for capital M. Okay. The feature that I'm looking for in this whole image is capital M. So I put my filter over here and I'm looking the whole image through this filter only. Through this filter, which is hidden throughout the filter, but only it finds one alphabet like this. So suppose I look through this filter, I find F, then I slide this filter over here, I find I, then I slide filter over here, find L, then T, then E, then R, S. I'm not looking anywhere else. I'm only looking through this filter. Then A, N, D, capital F E A T U R E. And as long as I'm not finding capital M, the feature or the pattern that I'm looking for, I will not raise any flag. I will not declare my success. However, as soon as I find capital M, you see, this is my filter, and through this filter I'm looking on this slide. As soon as I find capital M, since my name starts with M, I'm Munindra Oja. So as soon as I find M, I became very happy and I started exclaiming, I found M, victory declared, this, that, and I started shouting, exclaiming. Now, what is happening? This is the image, this whole is the image, this whole is the image, and you have one filter, and there are so many things written on this image, so many patterns on this image. But what am I actually looking for? I'm actually looking for only one thing, which is this kind of pattern, capital M. So if I find capital M, I will raise flag that yes, I found M over here. Okay. So there it is not possible that only one filter is required. Let someone else find some other filters. Okay. So let someone else find some other filter such that not only M is looked for, let someone else look for some other filter also. So let me create another filter, and through this filter I am looking at small e. Okay, so I take this filter and I put it over here because I found M at only one position. So this position was recorded. Now I take another filter, and through this filter I am looking for small e. So did I find E over here? No. I find E? No. I find E? No. Then I slide over here? No. Then I slide over here? Yes, I found E, small e. Okay, I declare that small e is present in this location, right? And at the same time, I keep marking also. I keep marking. So I had found capital M over here and small e over here. And through these filters, I keep on moving, and then I found an e over here. So again, I'll mark it this, right? And so on and so forth. Wherever I would find small e, let's say this is the location I found e, and I mark it over here. So what is happening? You see, there is an image, as you know, it's an image of the slide that I have created, and there are filters, several filters that I have created. I take each filter and look for a specific pattern. What that pattern would be, I'm not telling you. It could be any random pattern. I'm being very objective that it should be small e, it should be capital M, but doesn't care what neural network learns. So the pattern that I'm looking for is what I'm doing to find that pattern. I'm looking through filters. I created a filter which is specifically made to look for these patterns. I looked through these filters and found out the pattern. And wherever I find that pattern, I'll mark it. So the result of this filter and searching is a map on the whole image, which will have markings of these pattern, of the location of these pattern. So wherever I found E, I marked it over this as the map on the map, that this is the location of small e, this is the location of small e, this is the location of capital M, this is the location of small e, and similarly many filters would be there, and similarly many markings would be there, feature maps would be there. So I create a filter to find out the feature. And wherever I find the feature, I mark it as the location of the feature on the image. So the result is called a feature map. Now I come back to the content that is written on the slide. You see, I'm trying to find this kind of curve. Okay. So I am trying to find this kind of curve. And to find this curve, I need to prepare a filter. So what it says, it turns out that a filter is essentially a feature detector. Filter is essentially a feature detector. Let me create a filter like this, which will have all these zeros as a blocked out value. We have shaded. This is a shaded region. Okay, nothing is being seen through these pixel values. Nothing is being seen through this pixel value. What is being seen is through these pixel values which have a value of 30, 30, 30. Okay, let's move ahead. I take this filter. This is the filter that I created previously in the previous slide. This is the filter. Okay, I take this filter and I put it over here in this region. Of course, this is very big. So let me see that this is the filter. The yellow box is the filter. This matrix, the filter matrix that we created, is being represented by this yellow box, and I take this filter and put it over here in this location of the image. When I put it over here, what is the mathematical operation that is taking place? Mathematical operation says that this 0 multiplied with 30 gives me 0. This 30 multiplied with 0 gives me 0. This 0 multiplied with 50 and this 50, 0, both 0 gives me 0. However, this 50 multiplied with 30 gives me some value. Okay. Again, this 50 with 0 gives me 0. This 20, however, with 30 gives me some value. This 50 with 30 gives me some value. This 50 with 30 gives me some value. And this 30 with 50 gives me some value. And remaining becomes 0 because these are 0. All right. So these multiplications which happened, this is 0. This is totally 0. This part is totally 0. Okay. So these multiplication, this I think is also 0. So 1, 2, 3, 4, 5, 5 multiplication. 1, 2, 3, 4, 5 multiplications gave me some value, a large number. So as soon as I got a large number, what I said was I raise a flag that okay, yes, I got this feature, and immediately this large number indicates I got the feature. Okay, so this is the case about this portion of the image. Let's move on to another portion with the same filter. With the same filter, this filter, I take this image and put it over here in this region. However, you observe that none of the multiplication with these non-zero values with the image value give me any significant number. So multiplication and summation gives me 0. So the convolution process that I applied with this same filter in another region of the image gave me 0 value. So if it is not a large number, I don't get a flag raised that the result is finding of the same feature. So I did not find that feature over here. So now what I'm doing is that I am with this filter, I'm looking for certain features, and that is the job of every filter, to find out a certain feature in the image and specify what is the location of that feature. So when we perform, you see, when we perform these convolutions, what we do actually is that we have the image and we have the filter. So suppose this white portion is the blacked out, we are not able to see through this white, but we are able to see through these green shades. So there are two filters, and I apply this filter onto the image and I get a resultant feature map. So this is image. When applied with this filter, this is filter, I apply this filter onto, so I apply this filter onto this image and I get this feature map. This feature map just indicates where all I'm able to find the pattern that I'm looking for. What is the pattern I'm looking for? 2 pixels, black pixels in consecutive vertical section. Okay, 2 vertically adjacent black pixel. So if I take this filter and put over here, you see, then I'll be able to find this. Right, with this filter I was able to indicate that okay, 2 consecutive vertically adjacent pixels are present in this location, so this location is marked as black. Similarly, if you have this filter, what it will do, it is actually trying to find out 2 horizontally adjacent black pixels. So when I take this filter and I put it over here, then I find that yes, I represent it in this feature map, that I found this kind of arrangement, this kind of pattern. So as many filters, those many feature map. आपके पास जितने filter होंगे उतने ही feature map आपके बनेंगे. Suppose I take 10 filters, then I will have a resultant 10 feature map. Okay. So this operation is called convolution. We take a filter, we multiply it over the entire area of an input image. In this scheme, the layer of neuron is a feed-forward neural network, represent either the original image or the feature map. Filter represents combination of connections that get replicated across the entirety of the input. Now I tell you, just skipping this hand computation, I tell you how this concept is actually related to the neural network. You see, you all understand that in neural network, let me bring this image down a bit. Right. You see, now how do we apply convolution, concept of convolution onto the neural network so that we could create a convolutional neural network? First, I think you understood what is convolution. So if you have understood convolution, then let me apply the process of convolution onto convolutional neural network and then create the whole CNN. Right. Let me just zoom it a bit. Okay, now much better. You see, suppose I have this whole image. Okay, the input neurons that are depicted over here is actually an image, and this image is, I think, I don't count with counting the number of pixels, but let me say this is 20 by 30 pixel image. Okay, so 20 width and 30 height of the image. Now out of this image, I create a filter, a small 5 by 5 filter. This is 5 by 5 filter convolving around an input volume and producing an activation map. Yes, feature map is also called as an activation map. Okay, it activates itself, the neuron activates itself, so that is why it is called activation map. Most of the time it will be called feature map, but these terms are, I mean, every researcher loves to coin their own terms, and so activation map is also one of the name. I think, in my honest opinion, computer science would have been very user friendly or student friendly had these different names not been coined. People have stuck to simpler names, no? Computer science would have become more famous. Anyways, so you see, this is my whole image. This is a whole image. Let me just assume that it is 20 by 30. If anybody is free, they can count and tell me how many pixels there are actually. Let me use another color. Right. So now in this whole image, I take a small 5 by 5 filter and I put it over here. Just this. I put it over here and I perform the operation of convolution. Now, where is the filter values? You would ask me, from the tiny matrix, big matrix, I got the image pixels. Okay, for the tiny matrix, I am telling you that there is a tiny matrix, but where are the numerical values? Okay, you understand the concept of weight values, right, that are present on the edges connecting two neurons. Am I right? All of you understand the concept of weight values which are present on the edges. Somebody please answer me. Is it clear to you what is the meaning of weight value which is present on the edges? Okay, great. So see, the time matrix value that in the previous image I had shown to you was written with red color. Now here the tiny matrix values are actually the weight value which are present over these edges. These edges are there. You see these black edges emanating out of this 5 by 5 region and converging onto this small neuron of the first hidden layer. So let me explain this arrangement to you, and then I will talk about how convolution is being mapped on here. We take a 5 by 5 region of the input image, just this 5 by 5 region of the input image, and this 5 by 5 region is connected to a small single neuron of the first hidden layer. And how is it connected? All the 5 by 5 means 25 neurons or input values are connected to one single neuron. If it is connected to a single neuron, then there are edges with which it is connected. And okay, tell me, had it been a simple dense layer, simple multi-layer perceptron, MLP, you would agree with me that all the neurons of input should be connected to all the neurons of first hidden layer, right? It's a dense connected, fully connected layer. So if it is a regular multi-layer perceptron, then all the neurons of input layer should be connected to all the neurons of hidden layer. But this is not regular multi-layer perceptron. This is convolutional neural network. So in convolutional neural network, we don't connect all the neurons of input layer with all the neurons of hidden layer. Although I'm saying all the neurons of input layer, but in input layer, exactly, there are no neurons. They are just numerical values, the input values. So, and it is also written input neuron, but there is nothing like neuron in input layer. They are just values. So let me just talk about nodes. So all the nodes of input layer are not connected to all the nodes of hidden layer in case of a CNN. They are regionally connected. Let's say these 5 by 5 portion, this 25 neuron portion of input layer is connected to a single neuron. When this region shifts like this, then this neuron will also shift like this. Okay. When this region shifts like this, means the third set of 25 neuron, then third set of 25 neuron is connected to third neuron. When this region shifts from here to here, means the fourth set of 25 neuron, then fourth set of 25 neurons are connected to this neuron. So in convolutional neural network, first thing is that the connectivity is very local. It's regional. It's not global. It's not like all the neurons of input layer are connected to all the neurons of hidden layer. No, they are locally connected. What do we mean by local connection? Just like what I explained to you, a single portion of neurons is connected to a single neuron of the hidden layer. Now, how is convolution helping this? Convolution is helping in this fashion that, let's say I come back to my first neuron. Okay, I have weight values over this. I have weight values over this. So suppose I have 25 neurons. So of course 25 edges will be starting from input neuron and merging into the hidden layer, first neuron. So now 25 edges. So 25 edges means 25 weight values, 25 W values. Okay. Now every weight value is corresponding to every input neuron, right? How many input neurons are there? 25. How many weight values are there? 25. So don't you see the similarity of big matrix and tiny matrix? I have taken a small portion of this big matrix, okay, and what is the size of that portion? 25. I mean 5 by 5, okay. So 5 by 5 portion. 5 by 5 portion of this big matrix is being multiplied with 25 weight values. So every neuron input will multiply with its respective weight value. Okay. So suppose first one is x1, x1 is multiplied with w1. Then second input value is x2, x2 is multiplied with w2. Then third input value is x3, and that is multiplied with w3, and all of these are added together. You see, dot 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 plus, and let me just erase it. Plus x, I started with 1, so I'll write 25 into w 25. So what I'm doing over here, I'm taking one input value and multiplying with weight value, and one input value, weight value. And where are weights coming from? Let me say that weights are coming from tiny matrix. Okay. So these W1, W2, W3, all of them constitute the tiny matrix that I have fixed over here. W1, W2, dot 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 W25 at the very end. Okay, W25 at the very end. Dot 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 dot. So this is the matrix which I call the tiny matrix, the filter matrix, the convolutional matrix, whatever name you want to give to it. This is the matrix that I take and put it over here. And to map with the neural network architecture, I put these values on the edges connecting these neurons to the first hidden layer neuron. Now, when I multiply all of them, isn't it similar to a weighted sum of all the inputs? It's exactly that, right? I perform a dot product and I add all of these multiplications together. When I add all of these multiplication together, the effective mathematics behind is the weighted sum. All the inputs are being multiplied with certain weight values, numerical values, and they are added together. So this is equal to summation xi wi, right? Summation xi wi, and this is what? This is the z, the legend that we say. And job of a neuron is just to perform the weighted sum of all its input and then pass it on to an activation function. Suppose activation function is sigma, the sigmoid function, then he pass this z to sigma, and that produces an activation value. If the activation value is the z is greater than 0, there is a great possibility that sigma will produce 1, and if it is less than 0, it will produce 0. So if it is 1, the neuron will activate itself. That is why the term activation map. And if it is the input value is 0, the neuron will not activate itself. That is why the active, and it will not fire, not activate, and will not mark the presence of that feature. Okay, so when I'll find out the feature, I will immediately raise a flag. This is what I meant by that. As soon as I find a value which is greater than 0, I'll raise a flag that okay, I found this. And what does it mean by raising the flag? The output of my neuron activation function will be 1. If the value is not present, or somehow I find a negative value or 0 value, then I'll not raise the flag, I'll not activate the neuron. through the activation function, and the value will remain 0. So whichever neuron is activated, suppose this neuron is activated, this neuron is activated, this neuron is activated, all these activations will indicate presence of the feature that this filter is looking for. Similarly, as many filters as you want, you can have. Now, one more thing. When I say I have this filter, then definitely these weight values will not change if I take this filter and put it over here, let's say. When I put it over here, again, the weight values, these weight values will remain same. However, that is not the case in traditional neural networks. In traditional neural network, in conventional neural networks, the weight value with every edge changes. But in this case, your filter is same and you're looking for same pattern throughout the image. So you will have same weight values. Now, when the filter changes, the weight values also change. But for same filter, the weight values will remain same. I encourage you all to ask question wherever you feel there is a problem. So please ask question and then I'll be able to answer them accordingly. Okay. Many times we think that people understand what I'm saying because that's my ego. You should understand what I'm saying, right? But that is not the case. People don't understand. So not boasting into false egos, please ask question, and your question actually helped me understand what is that thing you are not getting. So I'll be able to modify my uh, method. Right. So still moving on with the convolutional layer. So what is happening is that you see. Somehow these slides are disturbed. I am sure what. 1 second. I'm looking for something else and I'm not finding. Filters and feature maps. So let me just so this operation called convolution, we take a filter, we multiply it over entire area of an input image. In this scheme, the layers of neuron in a feed-forward neural net represent either the original image or feature map. The filters represent combination of connections that get replicated across the entirety of the input. So you see, you understood how I applied convolution in the neural network and then created a concept of convolutional neural network. Now, as I told you, for one filter, the weight values remain same. So I'll take the same filter and convolve it over the whole image. I will slide it over the whole image and keep on ticking the part where I found the feature. So all those portions will be ticked. So to create a map of the presence of features in the image. Then I change my filter. I take another filter and with the new filter, I perform convolution on the whole image and I create another feature map. Then I take another filter and I convolve it over the image and I create another feature map. With every filter, I try to find out a new feature value. Okay. So as many filters you apply, those many features you would obtain. So the question is, how many filters should you apply? There is no fixed criteria. People tend to experiment with number of filters. You can increase the number of filters, that will increase the computational complexity of your model. You decrease the number of filters, that will decrease the identification ability of the model. So there is a balance which all designers, model developers have to build a balance. Okay. So you see this example in which first we have k kernels or k filters waiting to be applied to the image. So 1, 2, 3, 4. So let's say 4 filters are applied to the image. Image is same. So with 4 filters, I get 4 feature map. Okay. And output of each convolutional operation produces a 2D output called activation map or feature map. When I apply this filter to a 3-dimensional image, the image is not most of the time two-dimensional. It is many a times three-dimensional also. Why three dimension? Because if it is a grayscale image, then only I will have a two-dimensional image. Otherwise, with RGB image of the colored images, I will have a depth of colors. So red, green, blue, these three will form the depth of the image apart from height and width. Okay. So we understood this part, and let me move on over here, the local connectivity. Yes. So you see this is image, the red, green, blue RGB image is represented in a three-dimensional fashion, and I take a small portion, 3 by 3 portion of this image, I multiply or perform the convolution with this filter. So this gray portion is the filter representation. This gray part is multiplied with the RGB part, and result is a scalar value. Now remember one thing. When I apply a filter, the width and height of the filter are definitely smaller than the image. Okay, because it's a tiny matrix. I'm calling it a tiny matrix. So the width and height of the filter are smaller than the image, but the depth of the filter has to be exactly same as depth of the image. So if depth of the image is 3, the depth of the filter has also to be same size 3. So here by chance we have taken a width of 3 pixel, a height of 3 pixel, but by force we have to take a depth of 3 pixel because the image is of depth 3. So let's see over here, these are filter map, and there are some other properties of now with these arrangements. I explained to you what is convolution, I explained to you what is convolutional neural network. Now let me talk about many hyperparameters that are associated with convolutional neural network. One of it is spatial extent. Okay, spatial extent is a hyperparameter which is also called the receptive field or the filter size of the filter. In the first example that I gave you, I took a filter size of, let's say, which example I gave you, the example of, yeah, this. In this example, I gave you the tiny matrix size of 3 by 3. The tiny matrix, the yellow matrix, has a size of 3 pixel wide and 3 pixel high. Then I give you this filter in which I have 1, 2, 3, 4, 5, 6, 7 pixels height and 7 pixels wide. Okay, right. And now here I gave you 2 by 2 filter size. All of these are called filter sizes or receptive field size. Here, what was the size? The filter size is 5 by 5. I took a portion of 5 by 5. So all of these are called spatial extent or receptive field size or filter size. Most of the time you would hear this term filter size. What is the size of the filter? Size of the filter or spatial extent E is the height or width of the filter. I am saying height or width because it has been a convention, although this is not a written rule anywhere, but it is an unwritten rule that the size of the filter is always a square. Okay, filter is never taken to be a rectangle. Whenever you choose a filter, choose it to be a square. Why square? Because with one parameter only, the program will be able to understand the width and height. It doesn't require two different parameter values. If it is rectangle, you will have to specify the height and breadth. But if it is a square, you can do away with single value. So it is always taken as a square measurement, and then it is always taken as an odd numbered dimension. So odd number, 3 by 3, 5 by 5, 7 by 7, 11 by 11, because with that you will be able to easily identify the center of that filter. Okay, so if it is a 5 by 5, then definitely the center is of course one pixel, the unique pixel. This pixel is the center filter. So this becomes, if it is even, then you will have to specify 2 or 4 pixels as the center. But if the size is odd, let's say 5 by 5 or 3 by 3 or 7 by 7, then one pixel can uniquely be identified as center. Okay. So these are the two things which are associated with the parameter spatial extent. So you understood spatial extent. The second is depth. There are two types of depth. One is input depth, the other is output depth. Input depth is the depth of the input that is there. So whatever is the input, what is input? Input is the image at the very first step. Then output of first hidden layer is the input to second hidden layer. Then output of second hidden layer is input to third hidden layer, and so on. And output of last hidden layer is subsequently the input to output layer. Okay. So whatever be the depth of input, that is called the input depth. But whatever be the output of the convolution process, that is called the output depth. How do we know the input depth? Input depth is first defined by the depth of the image, because that is the first input. So input of image, depth of input image is the input depth at the very first step. And then after that, it is governed by whatever calculation you are performing in CNL. Okay. So input depth is in this scenario, as with this example, you see the input depth is 3 because this image has 3 channels, red, green and blue. However, the output depth is 1, 2, 3, 4, 5, 6 because there are 6 filters which are being applied to this image. So as many filters you apply, those many layers of output are created, and the depth is governed by the number of filters that we are applying. For this, let me annotate. So with this image, with this filter, I got this slice. Okay. With the same image, with this filter, I got this slice. With the same image, with this filter, I got this slice. With the same image, with this filter, I got this slice. With the same image, with this filter, I got this slice. And finally, with this image, with this filter, I got this slice. And combining all the slices together, I got a depth of 6. So output depth is governed by how many filters you are applying in the convolutional layer, and input is governed by what is the depth of the input that you are providing at that layer. Now suppose this is the output of first conv layer and it goes to H2. Suppose this is H2, the second hidden layer. Then for second hidden layer, the input depth is 6, as is governed by the first conv layer. The input depth is 6, and the output depth, what would be the output depth? The output depth would be decided by how many filters I apply over here. How many filters I apply over here, that would decide what would be the output depth. Okay. Stride is the step size, the size that you step size, the size of a step that you take to jump from jump your window. You are sliding your window, right? So in this example, in the animation, GIF animation that I had shown, I'm sliding my tiny matrix by 1 pixel at a time, from here to here, from here to here, here to here, here to here, then here, then here. Sorry, I stopped. First from I put it over here, then here, and then here. Okay, the 3 matrix. Then I take it here, then here, and here. Then I take it from here to here and here. So I jump 1 pixel at a time from left to right, and from top to bottom also I jump 1 pixel at a time. So my stride is 1. Stride is 1. If I jump 2 pixels, then I'll jump from here to here and my stride will be 2. And similarly, if I jump from left to right in 2 pixel, I'll have to jump from top to bottom also in 2 pixel and my stride would be 2. So if it is a 2 pixel, if it is 3 pixel, I mean 1 pixel, then I'm getting a resultant feature map of 3 by 3. Okay, because I have to make 1, 2 and 3 jumps, and from here also 1, 2 and 3 jumps. But if it is a 2 pixel stride, then how many jumps I'll make? First I present over here, then I jump over here, 2 jumps, and then top to bottom 1 present over here and then 1 present over here, 2 jumps. Okay, so it will be 2 by 2 matrix. So the feature map would be something like this. So you understand, if I have to make the output smaller, then I'll have to make our stride bigger, or vice versa. If the stride is bigger, the output is smaller. Okay, so if the stride is smaller, the output is bigger. Okay, so I explained to you what is stride. As it says over here, this will produce a smaller output volume, especially when the stride is 2, then filters jump 2 pixel at a time as we slide, right? So here it took 3, then it jumped from here to here, then it jumped from here to here, then here. How do you find out the spatial size of the output volume? This is a very well-known formula, W minus F plus 2P upon S plus 1, where W is the input volume size. Input volume means what is the width, height and width of the input. Okay. F is the receptive field size or filter size. P is the padding. I have not yet explained padding to you, but P is the padding. S is the stride that we take, and plus 1. What is padding? Padding, sometimes we do padding to make our life easier in some of the cases where we want the center of the filter to be at the first pixel. Suppose I have taken a 3 by 3 filter and I want my center to start from the very first pixel of the input volume. So what I'll do, I'll not have any value to multiply over here for this region. So what I'll do a padding. So suppose I can put 0, 0, 0, sorry, 0, 0, 0 and 0 like this. So all a new row and new column will be created which will have zeros. So this is called a padding of zeros or zero padding, in which we create altogether new cushion for my will be the center of the filter, and I'll be able to do this multiplication effectively, because if the values are not present, how will my convolution work? So this is just to help it. Okay, so this is zero padding. So your convolution layer takes these things in consideration. If I have to perform, these are the values that it takes. The bias is also one thing which is attached with every layer. So now let me just show you how a convolution layer is created. Okay, so you see left, each neuron in the convolutional layer is connected only to a local region in the input volume especially, but to the full depth. So this region is connected to this local region, but to the full depth. Means what is depth? Depth is the result of each filter. So of course each filter is being applied to that regional portion of the input volume. So this filter is multiplied over here, creates this volume. This filter multiplied to this region creates this. This filter multiplied to this region creates this slice, and so on. So there are 5 filters, 5 slices. What happens is that input comes from the neuron, the weight value is applied, and a weighted product is calculated. Similarly, for all the inputs, the weighted product will be calculated, and all of these are added together. When all of these are added together, WIXI along with a bias value is the resultant weighted sum. Now this resultant weighted sum is passed on to an activation function. Activation function can be sigmoid function, ReLU function, leaky ReLU, whatever the function might be. You need to specify at the convolution layer itself, you need to specify what would be your activation function. So you specify activation function, and then that activation function takes up the input weighted sum and produces an output. Activation layers, sometimes you specify the activation function within the conv layer. However, sometimes you need to specifically specify an activation layer of ReLU, LU, or leaky ReLU, or whatever function, activation function you want to apply. So you need to separately specify the activation layer also. Now, apart from, so this is the operation that takes place. This is the complete operation that takes place at the conv layer. Apart from convolution, there are certain other functionalities which are implemented through different set of layers. One of them is pooling layer. Okay. So let me just tell you what all different layers there are. There are different types of layers, like dense layer. Dense layer, you all understand, when the neurons are densely connected, fully connected to each other, that is called dense layer. Then there is a dropout layer, then pooling layer. Okay, convolution layer, I have already explained to you what is convolution layer, and now I will explain to you what is meaning of dropout layer and pooling layer. So when we have pooling, what do we do over here? Normally we apply pooling after a set of conv and ReLU layers. ReLU means activation function layer. So suppose this is the architecture of a convolutional neural network. The first layer is the input layer. After the first layer, this is now set of hidden layers. We don't call it hidden layer, we specify the explicit name of the functionality that is happening. So after input layer, let me just make it full screen. After the input layer, we have conv layer, which stands for convolution operation. Then we have ReLU layer. It means this is the layer at which the ReLU activation function is being applied. And after that, we see a pool layer. Pool layer is the layer in which we apply the pooling operation. Then you see this whole thing is being repeated again. This set is repeated again. Okay. So this set is repeated again. It can be repeated, this set can be repeated as many times as you want. But let us first understand the functionalities of these layers. Apart from pool, I'll also explain the dropout. Primary function of pool layer is to progressively reduce the spatial size of the input volume. So in a way, it is actually reducing the amount of data. So in a way, it is performing the dimensionality reduction for you. Or in a way, it is also performing a regularization for you. Okay, a kind of regularization. I would not go as to specify it as a regularizing step, but definitely it is going to help you in reducing the overfitting. Okay, pooling also helps in controlling overfitting. Now you see, what does it mean by pooling? We pool some data values together and choose one of them. What do we mean by that? Suppose my pooling size is 2 by 2. So I take this 2 by 2. Okay. And suppose the pooling operation is max pool. So what I'll do, I'll choose the maximum value out of these 4 and pass on to the resulting layer. So out of these 4, if I could say that which one is the blackest one, then I'll assume that blackest one is the maximum value, although it is not the case. But just assume that blackest one is the maximum value. So white, minimum value, gray, okay, somewhere in between, black is the maximum value. So I'll take the maximum number and pass it on to the result, pass it on as a result. Then I slide it over here. Okay, it is making a two-step jump. So it's making two-step jump. It comes over here. The maximum value is still white, so it comes over here as a white. Then I take it and jump 2 steps. My stride is 2 pixels, so I come over here. Out of 4 pixels, the maximum value is gray value, so this becomes gray. Okay, and same thing happens over here. When I take this region, consider this region, and out of this region, the maximum value is black value, which is given over here. So this is max pooling for you, in which we take the maximum value or of the pixels under consideration or input under consideration and pass it as a result. There is another which is called min pooling or average pooling. Actually, there is no utilization of min pooling, because in that case you will be almost destroying the whole data. But average pooling is one thing in which you take all 4 pixel value or all 4 values and calculate an average of it and then pass on the average. But most of the time you would find that max pooling is the more prevalent one rather than the other ways of pooling. You see, now this is the operation of max pooling. When we perform max pooling, again out of 4 pixels we are choosing only one, so we are downsampling the data, and you can also say we are destroying a whole lot of data. Almost 1/4 3/4 of the data is being destroyed. For every 4 pixel we choose only 1 pixel, so 3/4 of the data is being destroyed. 75% data is destroyed. So if it is 224 by 224 pixel high and wide, then 112 by 112 it is okay, it is out of 2 pixels, it's making a jump of 2 pixels, so it is only out of every 2 it is taking 1, so half, it is making it half, right? It's halving our, yeah, so it is doing every 2 pixel in this way and every 2 pixel this way. Yeah, so the dimension gets reduced by half. The for every 2 pixel wide, in the width wise, for every 2 pixel it is choosing 1 pixel, and for height wise also every 2 pixel it chooses 1 pixel, so half of the dimension is gone. So 224 by 224 becomes 112 by 112. Yeah, in fact it is 1/4 of the whole data only. So but dimension gets reduced by half in both directions. So if it is half in both directions, it's only 1/4 of the data. But depth remains same. Depth remains same because for every filter, if there are, let's say, 64 filters being applied, then in pool layer operation also, this pooling will be applied on all 64 layers, 64 slices. It's not like you will pool in the depth also, because you see every depth slice is a result of a filter operation, a convolution operation. That is important, because filters, what filters are doing, they are finding the features and depicting the presence of feature on the map. So every feature map is important. The length and height wise the features could be decreased, but depth wise we cannot eliminate any feature map, because that feature map was created by creating a filter. So max pooling is the way we do it, and again the size is determined by the same formula. And now here we don't do padding, so W minus F upon S plus 1 is the height and width that we obtain. And after that we apply a fully connected layer. So this is the architecture, the traditional architecture of convolutional neural network. When we have input layer, we have a convolution layer followed by an activation function layer. Here we using a ReLU function. So conv ReLU, and after conv ReLU we apply the pooling operation. Okay, so once conv ReLU pool is replicated as many times as you want, then at the end, towards the end of the CNN architecture, you apply fully connected layers. Fully connected layers are very beneficial when you want to extract features out of the processing, the whole processing of the image. So You see, fully connected layers are only vectors. They are not two-dimensional, just like we have been seeing in other conv layer, ReLU layer, pool layer, then feature map. All these are two-dimensional or three-dimensional. Our fully connected layers are one dimension only. They are vectors. Okay. So if they are vectors, then a vector is a better representation of a feature, set of feature, rather than a two-dimensional image or three-dimensional image. So at the end, we apply a fully connected layer, apply one or two fully connected layer to identify the set of feature, and from that fully connected layer, we perform a final output layering, and the output layer, depending upon how many classes there are, you can have one output neuron or multiple output neuron, depending upon as many classes as you have. But between two fully connected layers, there is a concept of dropout also. We apply dropout between fully connected layers. How do we apply dropout and why we apply dropout? Dropout is a process of regularization. It's actually a regularization procedure. So you would have studied about L1 regularization, L2 regularization, and similarly in machine learning also we have different regularization techniques. In deep learning, we have dropout as a regularization, in which regularization technique, in which what we do is that we randomly switch off some of the neurons. We don't delete neurons, we don't change the structure of the network, we just randomly switch off some of the neurons. So when we switch off the neuron, as you can see, imagine these are the neurons. These are the bulbs which are illuminating your home. To save power, or probably to make a uniform light throughout the home, you might experiment with some of the bulbs which you switch off and switch on at random location, random interval or random time. Similarly, what we are doing over here is that, and when we switch off the bulb, we don't actually dismantle the bulb, we don't actually dismantle the switches, we don't dismantle the whole wiring. We just utilize the switch and we switch off. The same thing is happening here also. These neurons, these connections, these edges are all here. We just randomly, with certain probability, we randomly switch off certain number of neurons and their activities. We switch off the activities, but it does not change the overall architecture. Why do we do it? We do it to promote robustness in the network. How does it happen? Suppose, look at this example. Suppose the first layer over here, the first hidden layer has 5 neurons, and out of 5 neurons, I switched off 2 neurons. If I switch off 2 neurons and again train the network, then remaining 3 neurons will have the responsibility of learning the pattern that is being given to neural network. In the second hidden layer, I have switched off 3 neurons. So only 2 neurons will have the complete responsibility of learning the pattern. And again in third hidden layer, again I have switched off 2 neurons. So 3 neurons will have the responsibility of learning the whole pattern. So you see, out of 5 threes are 15 neurons, I have switched off almost half, means 7 neurons have been switched off. So the network which was supposed to function with 15 neurons is functioning at half its capacity with 8 neurons only, but still with 8 neurons it is being forced to learn the same pattern. Okay. The idea over here is that if this neuron can identify a pattern and this has become an expert in identify the pattern, why don't we promote this neuron also to identify similar pattern? So when in the case of generalization, it doesn't happen that this neuron is the only determiner that what would be the pattern, what would be the output. This neuron also has a vote, also has a word, also has a say in what is the pattern. If only one neuron learns the pattern, there is a possibility that overfitting might happen because it is learning too much. It is becoming very trained in identifying a pattern and it is not looking around. But when we have a democratic nature, when we have more than one neuron to say or vote or to determine what is the pattern, then probably their combined effect will be considered by the network to judge what is the pattern present in the image. And this way, the network will be more stronger in generalizing, in determining patterns in a totally unknown, a new image that is given to us. Okay, so overfitting will be reduced over here. Take another example. In a team of suppose 15 people, if one person falls sick, then others should be there, other members of the team should be enabled or should be present so that they can take up the responsibility of performing the task of the person who has fallen sick. Otherwise, the functionality will stop, the efficiency of the team will decrease. So in a way, if this neuron is not present, I am making this neuron more robust and the whole network more robust, such that if one neuron is not able to function properly, the other neurons will take up its responsibility and perform to the expectation of the network. So my network is becoming more robust. So that is the objective of dropout, and dropout percentage is again a hyperparameter that we need to specify what will be the parameter. We can make it 0.1, 0.2, 0.3, whatever. Okay. And this way we specify what percentage of neuron will be switched off. And it is a random process. In one batch of training, it could be these neurons which are switched off. In another batch of training, it could be randomly selected some other neuron which could be switched off, no one knows. Okay, so it's randomly selected which neuron will be switched off, which neuron will activate themselves or remain active. So with this I have explained almost all the layers, and now you see what is the layer pattern. Yeah, so this is a traditional layering pattern of convolutional layer where we have input followed by conv-ReLU combination. This combination cannot be separated because ultimately conv is only weighted sum. ReLU is the activation function which makes it a complete neuron or a neural network layer. So conv-ReLU is a combination. It can be repeated n times where n ranges between 0 to 3. Then you apply pool layer. There's a question mark behind pool layer which says that it's optional. You can apply pool or you can choose not to apply pool. Okay, but this combination, if you apply pool or don't apply pool, you can apply it m times where m is greater than 0, means of course you need to have it once, and after that you can have as many conv-ReLU pool, conv-ReLU pool combination as you want, infinite number of times. After that, towards the end, you apply an FC. FC normally ranges from 0 to 2, means 2 fully connected layers are there. And between FC, we apply a dropout. Okay, with every FC, we apply a dropout. The traditional layer patterns are like this. We have LXNet, in which this is the combination of LXNet architecture, which has multiple conv-ReLU pool layer set followed by FC layer. You see input followed by conv-ReLU pool 2 times, then conv-ReLU 3 times, then 1 time pool, followed by fully connected ReLU and dropout. This is repeated 2 times, and then finally a softmax function at the output layer. For deeper architecture like VGGNet, which is a very deep architecture, we stack 2 or more layers before every pool layer. So you see conv-ReLU 2 times, then a pool, conv-ReLU 2 times, then a pool, conv-ReLU 3 times, then a pool, conv-ReLU 3 times, then a pool, and finally fully connected layer 2 times. And between 2 fully connected, we have a dropout. So it is repeated 2 times, and finally the output is represented with a softmax function. We take the softmax function and apply on the output layer. So these are different case studies associated with LXNet, LeNet, ZFNet, and this ZFNet was the ILSVRC 2013 winner from Matthew Zeeler and Rob Fergus. It became known as the ZFNet, short for Zeeler and FergusNet. It is also giving very good result. The LXNet was given in 2012, and the Alex Krzyzewski and Geoffrey Hinton group, and they are the pioneer of convolutional neural network. However, Jan LeCun in 1990 actually gave the convolution idea of convolution neural network. But you see why these gaps of 1990s and then 2012, almost 22 years of gap. Why this gap in the development of such neural network, and why after 2012 we started getting so many different deep learning networks? There are certain things which actually started the advent of deep learning revolution, and the biggest of it is the creation of GPU cards. Towards 2000, end of 2007, NVIDIA came up with their GPU card, GPU graphics processing unit card, which was an excellent machine in performing parallel processing. The parallel processing which was applied and executed by GPU card inspired neural network researchers to apply their neural network functionality on GPUs and then perform these implementation. You see, before 2007, when we would apply neural network, we would use MATLAB as the most advanced software, and we would use serial machines, although some parallel processing was there in CPU, but CPU had many things to do. CPU was not independently executing our functions, mathematical function. So we would apply these big algorithms over CPU, and we would have to wait for months to get our output. And by that time, when we get our output, the whole motivation of the research was gone. The spark of idea that you had and why did you think of this idea was gone, and the output was very slow in coming. So when by the time you get the output, your idea is already gone and you don't have any inspiration, motivation to continue the neural network research. But with GPU implementation, people started getting result of their implementation very fast. So if you apply an algorithm and immediately get the output, you are either it is resulting good or bad or whatever be the result, you are getting the output. So once you get the output, you can tweak your algorithm and come up with a new algorithm. So this way people started experimenting in a big way, and they started implementing all the concepts that were given previously, like convolutional neural network, convolutional network concept given by Jan LeCun in 1990, and with that they came up with this LXNet and created convolutional neural network in 2012. And then after that, flood gates opened. So that is all from my side for this lecture. I hope we have questions, and I am open. If you have any question, probably we can uh, discuss.
So
Anyone,
any
any question?
participant, please. Yeah, some question is there, I think so.
My screen has hung up. Sir, if you could read the question, my screen is hung, so I'm not able to.
I think it is feedback. Thanks for teaching the complete architecture. Regarding the implementation, how to implement, they are asking how to implement all those things by using Keras.
Okay, I think that would require another session, and um, I think probably okay. In the next lecture, I will give a very brief demo of how to implement convolutional neural network through Keras. Okay, I'll be able to. I think I'll be able to answer the question.
I think all the participants have gone through the lecture and all have enjoyed, and you can see the feedback they are sharing. They have enjoyed a lot, and this time all the participants are very vigilant
Acha,
and they
I think, sir, this question is related to smartphone. Yes, for a smartphone, you see, deep learning is not and not an algorithm which could be easily or lightly implemented. It's not a light algorithm. First of all, so but there are two things in the algorithm learning. One is learning, and the other is implementation. For learning, you definitely need heavy duty machine, high performance computing. But for implementation, if you have a very small model, and these models once trained, they take up somewhere around 500, 600 MB of size, okay, disk space. So you can take up those models and through the lightweight TensorFlow, the TensorFlow has come up with new versions of lightweight TensorFlow. Through that, you can implement it on Android as well. But I think that is not part of the tutorial that we will be discussing.
So one question is there any other algorithm other than CNN for image processing?
See, you can apply any algorithm. In deep learning, the most advanced version is convolutional neural network, and apart from CNN, there are different flavors of CNN also. Even multi-layer perceptron you can also apply for vision processing. Then 2D and 3D CNN is also present, but it all depends upon the convolution process. The process of convolution is important, and you can have different connections in neural network. What I say is all the time is there are separate functionalities of the neural network. One is the functionality of neuron. What is neuron performing? The other is how the neuron is performing. Means is it performing independently, or is it performing in relation with other neurons, or and then the network, how the network is connected. So network is connected to all the neurons, and network is connected to some neuron. Then apart from this, that whether the network is working independently or in addition with other networks also. So you can have one network, you can have multiple networks also. So all these are different combinations, but the core idea is convolution, and that is fundamental. That does not change. So all computer vision problems have to rely on this process of convolution that is there. But convolution you can apply as many ways as you want.
There was another question, sir. For video captioning, which model should be suitable for video captioning?
See, video captioning is a very straightforward thing. First of all, you need to understand the object, okay? The object in the image, and then the relation between images, and then you need to convert this understanding into sentences, natural language sentences. So the job, it is cut out for you. The task is cut out. Identification of the object, relation between objects, and the natural language creation for those objects. But unfortunately, these things are not easy. Object identification is easy, but how do you find out a relation between objects? That is not easy. Then creating sentences out of those relation is also not easy. That is natural language processing. For object identification, we have CNNs. For relation between objects, that is also can be done using CNN. For natural language processing, we have RNN and LSTM, and GRUs are also there, gated recurrent units. So these are the three types of model which combine together to create captioning. And then another question, corner rounding issue for image processing is present in the convolution. Corner rounding can be removed with the padding that I explained. If you want to put the corners over there and implement the effect of corner and take the effect of corner, then you can implement padding, and with padding you can overcome this problem.
Say the next question.
If we have to compare two
Yeah, two image, which
Mhm.
then which model is suitable?
What is the purpose of comparing two images? I mean, comparing two images just for the sake of finding similarity or dissimilarity, then I think when you are looking at an image, no algorithm is better than CNN. And when comparing two images, I think again you are trying to find out all the features of both images and then match both of them. So I think, in my opinion, you take two images, feed to the neural network, find out their uh, last fully connected layer value, like feature value, and compare the two feature vectors. Okay, so as I told you, the last fully connected layer is most of the time referred to as feature vector of the image. So take an image, feed it to neural network CNN, and find out the feature vector and compare two feature vectors. If both image feature vectors are same, then image should be same. Otherwise, the image should be different. But that is a very naive method, because the whole neural network is a stochastic algorithm. It's not necessary that the feature vector created for image will be same if you feed the same image again and again and again. Okay, so you'll have to find out the percentage similarity. It can never be certain that percentage similarity will be the actual similarity, because in machine learning and deep network machine learning and artificial intelligence, we always talk about percentage accuracy. Even if two images are exactly same, or if I say that I'm feeding same image again and again, then it might happen that one image fed 10 times will result in 10 different feature vector. Okay, so it's always percentage which will tell you how similar two images are. There is no talk of 100% guarantee. Okay.
So, sir, thank you. Our time is also over. It was very long 2 hour session. So, because we are going to meet again at 3 o'clock, so it's better to have a break for a lunch. So, thank you, sir. We will meet again, all the participants, 3 p.m. today again for the others are going to be take the next session. Thank you. Thank you, sir. Thank you.
Thank you, sir. Thank you so much.